conference. I want to go to a conference. Like the
All right. 29th today. All right. So I think this is where we left off, right? Why are we like maximized? Right, so let's go through how to do this. Wow, our studio didn't open up yet? Jeez. Try this again. There it is. This is 29, 12, 3. I guess we already did this one. I think we did. So given the data and the mean, so here I can convert that table to a vector, called it males. Calculate the mean of the males is 2.82 males out of a clutch of 7. So the probability of being male then is that mean 2.82 divided by the 7. That's our out of number. All right. And then from there I use dbinom. Dbinom from 0 to 7. Clutch size is 7, the out of 7, with the probability of mean of the males divided by 7. That's our probability, which was 40%. And then, so that was our probability, so that's what these are. And then the expected number is the probability times the total number of clutches that we counted. All right, so we could do that a couple different ways. To figure out, what the clutches was. I used length of that vector since we didn't have any missing data in that vector. So I did the length of that and just multiplied that by the dbinom, and then I rounded to make sure I had whole numbers, and that's our expected numbers. Or that's our expected number of clutches with 0 males and 1 male and 2 male and 3 males. And then if we ask the question, is the probability of being male equal to 5/7, then we just change the prob and get our probabilities and do the same thing to get our expected, and we get these numbers. So I think we had Excel and we did side by side to kind of look at which one was most likely. So I think this way, when we use the mean, it really did look like our data were random. That it followed a binomial distribution with a probability of being male of 40%. If we compared our observed data to what we would expect the probability of being male is 5/7, then we see, yeah, it doesn't look like the probability of being male is 5/7. It looks like it's being less. So, all right, that's our binomial distribution. The distribution binomial was all probability of number of successes out of some number of trials. Poisson distribution is similar yet different. All right? It's similar yet different. It is used for rare events in general. And what that means with the rare events is that our out of number would be assumed to be infinite. So much so that when we ask for probabilities using the Poisson distribution, we don't give an out of number. We just ask, what's the probability of X successes? What's the probability of this number of failures? And so forth. We don't give an out of number. All right? And that's where it is. It's used to model events that don't have a fixed sample size. So the rare events assume that our total sample size is really large. All right? But in some cases, we know that total sample size really is not fixed. It's infinity. So we can ask the question, what's the probability that we'll have 2 phone calls on this phone right here? We didn't set a time frame. We didn't set a time limit. So that probability distribution is actually a Poisson distribution. All right. So we can utilize the binomial distribution to approximate the Poisson if we have the probability of our success being less than 0.1 and if our n times p is less than 5. This normally doesn't happen. I mean, we could, but if we know it follows the Poisson distribution, I say let's utilize the Poisson distribution. So in biology, when do we encounter this type of distribution? We encounter it whenever we're looking at spatial and temporal samples. All right, and when we're interested in spatial and temporal samples, we're usually interested in randomness. So for spatial samples, we're talking about distribution across a landscape. Are individuals randomly distributed across a landscape, or do they show some pattern? All right, that's a Poisson distribution. For temporal, we're looking at time to events. All right, how long, what's the probability that our individual will die 5 days after being infected? Well, they could die at, 1 day, 2 day, 3 day, 4 day, 5 day, maybe 6 day, 7 day, 8 day, 9 day, or they might not ever die. So it could be infinite. All right, so when we work with the Poisson, it's going to be distribution across the landscape or one of these time to event. And we're going to have examples of both. All right, so with our Poisson distribution, we have a couple of things that fall. One is that the average is going to be less than the maximum. So that the average number of successes is going to be less than the maximum number of successes, or even the maximum number of tries that we get. So that, by definition, then gives us a rare event. So trees in a grid is a good example. It's a spatial distribution. All right, I've got my box up there that shows a random distribution of points. And what we could say is we would go out to this area with our GPS. We go to every tree and we mark GPS locations, and then we came in and we plotted it on the grid. And we look at this and we ask, are these randomly distributed across the landscape? Well, we can do it using our GIS. We can do it using R, believe it or not, if we have our XY locations, right? Or we can do it by hand. So we can blow this up to the sides of this room, all right, and lay it down. And what we could do is use the actual tiles as our grids, as our squares. And what we do is we count up the squares, or we go square by square, and we count up how many trees actually fall within those squares. So we're going to have squares that have 0 trees. All right, we're going to have squares that has 1 tree with 2 trees. We can have squares in theory with 100 trees, or possibly an infinite number of trees. But what we get is we base our square size such that the average number of trees per grid is less than the maximum number that could fit. So we produce this rare type of event, which thus allows us to use a Poisson distribution to assess, are our trees randomly distributed or not? Yes or no? All right. We also have a situation where the occurrence of events must be independent of prior occurrences. All right, so what this says for our tree example is that once we find a tree, the probability of finding another tree is independent of the fact that that tree exists. All right, so the probability of finding a tree is independent of everyone else's location. Once we find one, we can't increase or decrease the probability of finding another tree. The implications of this is that if this is met, then we are following the Poisson distribution. We do have this random association. But if we violate it, let's say we find a tree, and then that increases the chances that we're going to find more close by, which would kind of make sense when you think about trees are going to drop seeds. Seeds are going to germinate close to that parent plant, right? And what happens then is our trees are no longer randomly distributed, but then we start to say that our trees are actually clumped together or aggregated together. So we violate. We can still use a Poisson distribution to do this, but we're basically concluding, okay, this is not Poisson distribution, so we're not randomly distributed. Instead, we're clumped or aggregated. And that would follow a different type of distribution. Right? If we find a tree and it's unlikely to find another one close by, we're also violating this independence situation. And thus what we end up seeing is something more of a uniform distribution. We can see this in nature, right? We can see this in cropland. Right? So go to the Cristobal Christmas tree farms. The trees are evenly spaced. It's a uniform distribution. If you find one here, you're not going to find another one really close by. It's going to be a set space apart from it. Is it a random distribution? Is it a Poisson distribution? No. It follows a different distribution. All right. So here's examples of clumped and uniform, what we would look like. When we generate our expected frequencies, our expected distributions, we're comparing our Poisson to what we observe. So if we observe a clumped distribution, what we end up seeing is more in the tails. So you can imagine, if we took this part, blew it up, overlaid it here, we're going to have some of these grids that have a whole lot of trees in it. They've caught a bunch of these trees together. And then you're going to have a bunch of grids that have a bunch of zeros in it, all in this blank spots. So we have an overabundance in our tails. So let's kind of draw what a Poisson distribution might look like. So a Poisson distribution might look something like that. All right? If we are clumped, we have more in the tails, which means we're more like that. We're under present in the middle part of our distribution, and then we're over again in the tails. So we have an excess of zeros and an excess of our large numbers. That's our clumped or aggregated distribution. Now, what produces that? Number of situations. All right, it could be difference between good habitat and bad habitat. So our plants grow in good habitats and they can't survive in these poor habitat areas. It could be a consequence of dispersal ability of our plants. All right, who knows? We can look into that more. When we have this situation, because we have an overabundance in our tails, it's going to cause our variance to be larger than our mean. All right, so here I give your standard deviation. Standard deviation is going to be larger than the mean. I'm going to change that, actually put it as the variance, because that's what we want. I'm not going to be able to change that. That's squared. Looking ahead. Yeah, so we're going to say our variance is larger than our mean. S also applies, standard deviation also applies. But I'm going to put it as a variance because we can use the variance to mean ratio as an approximation of what our dispersion pattern is. We'll see that. All right. In a uniform or repulsed distribution, we've got more observed in our center than what we expect. So you've got fewer in the tails. So here's our example distribution again. Here's our Poisson. Now what we're dealing with is something like this. More broader, I guess maybe broader in the middle part, and then we're underrepresented in our tail. Examples in a spatial pattern would be like a uniform type of environment, or a homogeneous environment where it doesn't really matter where the tree lands, it's going to be able to survive. The other situation with this, in order to get this in nature, usually you need to have some sort of negative interactions between these individuals so that you can stay spaced. We can generate this artificially in, when we have these orchards, these farms and stuff. In nature, you really need the repulsion to happen, which you think of for penguins. Probably seeing all those penguins out. Yeah, they're wings length apart. Right? They're extremely territorial. Nothing's going to get inside their space. So they have a very uniform distribution pattern. All right. When we have this, since we're closer in our middle, we're going to have less dispersion than expected. So our variance is going to be less than our mean. All right. Questions? So how do we model it? We can calculate this by hand fairly easily using this equation. So the probability that we have X number of successes, and again, I didn't say out of anything, I just said X number of successes, is equal to lambda raised to the X over X factorial e to the lambda, where X is our number of successes that we're trying to find, lambda is the mean number of events per sampling period or unit, and e is our exponent, exp. All right, so we could do this, and I can show you how we get to there, how we can get to this process. But we're going to use R. So we had dbinom for the binomial distribution. We also have a dpois for the Poisson distribution, and it works the same way, just like the R poise and the P poise and the Q poise and so forth. Dpois is actually going to calculate our probability. Now, this function requires the number of successes, requires our X, and it also requires lambda, which is the mean number of events per sampling period. So for a spatial one, it's the mean number of trees per grid. Right? Or for a time to event, it could be the average number of seconds between phone calls. All right. Our expected numbers do use a sample size. All right. And that's how many total events we observed, how many total grids we counted. All right. And we calculate it the same way, n times the probability of that success, just like we did with our binomial distribution. So, as an example, we infect 10 chickens with a highly pathogenic influenza virus, so an H5N1 virus. All right, and what we're going to do is record when they die, what day they die. So again, we don't have an out of period. Yeah, we stop the experiment after, let's say, 14 days. All right, but we can let them go on. If they keep living, we just let them live the rest of their life. We can't. All right, so we infected 10 chickens, and we can calculate the probability that they die on day 1, day 2, day 3, day 4, day 5. All right. So based on those probabilities, then we would multiply by 10 chickens to figure out how many chickens do we expect to die on day 1, how many do we expect to die on day 2, on day 3, and so forth. And eventually, we'll get to the point where we've reached all 10 of our chickens, because that is our conventional sample size in this experiment. But our day to death could be infinite, could be unlimited. So here's an example of that. All right. So this time I'm bumping it up to 20 chickens. All right, we infected with a highly pathogenic H5N1 virus, and we record the day of death. All right. So what we want to do is calculate the probability of death and then the expected number of deaths that would occur on each of these days. And we've got this frequency table. So for the frequency table, I'm just going to clarify a little bit. All right. Day 0, we infect the chickens, and we start monitoring. So if they die within that first 24-hour period, it's day 0. If it dies between 24 and 48, that's day 1 and so forth. So in this case, we had 3 chickens that died within 24 hours of infection. We had 9 chickens that died in that after 1 day. We had 7 that died after 2 days and 1 that died after 3 days. Pretty highly pathogenic virus for a 20. So how do we calculate our probabilities and our expected values? Well, we're going to do it the same way as we did with the binomial, but we're going to use Poisson distribution. So I got my R. What I am going to do first is generate my vector. Okay. This is H5N1 example. Let me get this in here because I need to see these numbers. All right, I have mine. Leave this up for you. Type this out. All right. So, move this over. I had a little bit of stuff here. So in my R markdown, we're starting off with Poisson now. So got that listed as our header. Kind of gave a summary of when we use it. It's classically used for our spatial distributions and the time to event type situations. Time to event situations. So for the H5N1 example, I generated a vector from a frequency table. And then this one I wanted to avoid just using X alone. You can. So I'm just going to use XX, double X here. So XX, here's my X's. F is my frequency column. Why did I include a 0? I know the 0's in the frequency table. Could I make this vector and just leave the 0 off?
The F vector?
Yep.
That's only data on day 4.
What's that?
No, because you need something to go along with day 4.
Yeah. If I drop the 0, I have to drop the 4. Yeah, you're right. You'll get if you do that and use the ref, it'll say something like the vectors are unequal lengths. Actually, let's see what it actually, it'll say something like that. It should. Yep. Invalid times argument. And what that's mean, again, this is kind of vague, but that'll happen if you pass it like a text, or in this case where we have a missing vector. So these need to be the same size. So we have 5 items in the double X's, we've got 5 items in the time, it'll work now. So I've got my vector. So we generated a vector from the frequency table. So next thing we need lambda. So we'll use the vector. So we'll use the new vector and calculate its average. So mean of day is 1.3. So lambda is the mean. All right. So our lambda is 1.3, and what does that mean? It means we expect chickens to die on day 1.3.
Is there another way to word that?
Yep. Then we had to try to type it out. This is the mean day of death for our sample. It's the mean day of death. Thus, if we infect a chicken, we expect it to die on day 1.3 or 1.3 days. Die in 1.3 days. Die in 1.3 days. And this would apply for any of these time to events. So survival curves are based on that. Is that better? It kind of makes a little bit more sense. We'll also have lambda for spatial distributions. So just remind me to get that, to define that average as well. Mean day of death is 1.3. All right, so once we have lambda, so now that we have lambda, we can calculate the probability of dying on each day. All right, so we use dpois x lambda and this will calculate the probability of dying on day X if the average day of death is lambda. All right, so we're going to use dpois. All right, I can use the XX vector, or I can just use the 4 from 1 to 4. And I'm going to say lambda equals, and I'm going to do mean of day. So in this case, I could just use 1.3, no problem, because it's easy. But sometimes you're going to get a repeating decimal. Just use mean of that vector. So when we get this, we've got day 0, day 1, day 2, day 3, day 4. If our average day of death is 1.3, then we should see the highest probabilities around that period, around that mark. So 1.3 is closer to 1, so our highest probability should be on day 1. Now we still have, if we think of the curve, we're still going up a little bit. We can still go up, but this is discrete distribution. All right, this is a discrete distribution. So we don't really find the probability of dying on day 1.1 or 1.2. It's going to be a whole number, 0, 1, 2, 3, 4, 5, 6. Because that's how we end up doing it. We're not monitoring the chicken 24/7. In this case, when you do a high path, you have to check on them every 12 hours. So that's kind of how you get what day they're going to die. So this kind of makes sense. This makes sense. So now with the probabilities, so we use the probabilities to calculate the expected number of chickens that will die on each day, assuming we initially infected 20 chickens. So we had 20 chickens, and I'm going to start with round, all right? So if our sample size is 20, and that's in our table, that is the sum of the f vector. And then I'm going to use the poise that we just did. I'm just going to copy that and paste that down here. And I'm going to round it to 0. Because I don't want partial chickens. I want partial chickens. So that's our expected count. And that would be the expected count that we would put on our frequency table here. So 57521. And in this table then we have our observed, which is the number of chickens. We have our expected, which is that E column. Then we could do our chi-square test. Observed minus expected squared over the expected. And we'll learn how to do those. So we'll come back to all of this. All right. Could we get fractions? Could we get fractions? So if we said 1.3, where lambda is equal to 1.3? No, we can't. Because again, even though I draw this as a curve, a better way is probably to draw it more as kind of a histogram, or probably even a bar plot. Something like that. Or a bar plot. Because we're dealing with discrete data, whole numbers only. So yeah, don't try to use decimals. You'll get that error that says it's not an integer. So I'm just going to make a note here. Note, this is a discrete distribution. Therefore, we cannot calculate the probability of fractions. Fractions / decimals. Do that. All right, so just kind of get it in there. You have it in your notes. So if you try to do this sometime on your own, you get an error message. Now you know why. See. All right. And it works any decimal or fraction, you'll get the error. It has to be a whole number. All right. All right, Poisson distribution is discrete. All right, and it's defined by the lambda. It's defined by lambda. And lambda is their mean. All right, lambda is the mean. And the lambda is not restricted to integer values. So if lambda is a continuous value, that means we have an infinite number of curves, infinite number of frequency curves in our Poisson distribution. And again, we model it, we show it as a curve, but in reality, it's discrete. So we're going to have discrete boxes, discrete categories. Interesting point of the Poisson distribution is that the variance and the mean are equal. All right, so that the variance and the mean are equal for our Poisson distribution. So using this bit of information, we can use the variance and the mean to get an approximation of our dispersion pattern. And that is our coefficient of dispersion, CD. So we had CV. What is CV? Coefficient of variation, right? Now this is CD, coefficient of dispersion. All right, so we can take our variance and divide it by the mean. If they are equal, then our coefficient of dispersion will be equal to 1. And it suggests a random dispersion pattern, Poisson distribution. If our coefficient of dispersion is greater than 1, then we have more dispersion than expected. We got this situation where you have an excess of those zeros and an excess of the big values. All right, and that suggests we have an aggregator or clump distribution. If our coefficient of dispersion, variance to mean ratio, is less than 1, then we have a uniform or repulse situation. So we have a situation where we have an excess of all of those middle values that are going to be closer to our mean. Do we just use this arbitrarily? No, we don't. We will for now. But once we get to the chi-squared test, the goodness of fit test, the procedure is to first test if our data are actually Poisson distribution using a chi-squared test or a g-test, some sort of goodness of fit test. If we determine that this is not following what's predicted from a Poisson distribution, then what we could do is calculate the coefficient of dispersion to decide, well, are we clumped or are we uniform distribution? We'll do that near the end of the semester. But for now, just know this relationship, know what it means, know what these types of distributions are, all right? And if I say you get a coefficient of dispersion of 1.3, what's the dispersion pattern? You should be able to say it's clumped or aggregated, and so forth. All right, so here's practice for Poisson. All right, we've got two different situations. So one, you're going to calculate probabilities and expected values given the data. And then the second one is you'll calculate the probabilities and expected values given a mean of 3. So here's our trees in a grid. So what we've done is we've dropped grids. We've counted how many trees we found in each grid. We repeated it for however many grids we've counted. 100 maybe? 100 grids. So some of the grids had 0 trees, some had 1, some had 2, some had 3, some had 4, and so forth. Let's go ahead and do that. I'll work on mine. How's it going? Over. All right, so we start with generating a vector from the frequency table. We've done that, use the rep function. And then we're going to calculate the probabilities in E of x given the data. This approach, given the data, is used to answer the question, are the trees randomly distributed across a landscape? We would do this first before we would look at a coefficient of dispersion. So there's no way to really prove that it follows a certain distribution, but we can reject it. So we have to first reject that it's not randomly distributed across the landscape before we can then look at the coefficient of dispersion and make a claim that it's uniform or correct. So I use dpois, c is 0 to 8, lambda is mean of the trees vector. So I pass that right to it. And then the expected, I use the round. This time, instead of using length of trees, I use sum of my frequency. That'll work. It's the same number. Times are dpois lambda mean of trees. And I round it to whole numbers so I get these numbers, which incidentally are the same numbers that are in our frequency table. All right, so are the trees randomly distributed? Yeah, they're exact. They're exact. So then the next part is calculate the probabilities and E of x if the mean number of trees per grid is 3. So our lambda for spatial is average number of trees per grid, since we established grids and we counted the number of grids and so forth. All right, I used the same equations. I actually copied and pasted from here, right down here, and then I just changed what my lambda was. So lambda equals 3 for both of those. This type of question, again, or this approach answers the question, is the mean number of trees per grid equal to 3? So now we're not asking if it follows a Poisson distribution. We're saying, okay, we've done this before. Maybe in fall of last year, we did this study and we had a mean of 3. And then we go out and do this again this year and we say, okay, is our mean number of trees per grid equal to 3? Does that match what we saw last year? That's the type of question that we would answer using this approach. And what you'll see is that it's different. So I'm just going to move the Excel over here. So you can see the number of grids given the data. That's our observed. This is given the data. They're identical. But if we increase the mean number of trees per grid to 3, you can see that we have a shift in our peak. So our peak is kind of centered around here, around 2 trees per grid. Now we've shifted it down to 3 trees per grid. And if we're going to shift it, we cause that shift this way, we're going to have fewer trees, fewer expected trees down at the lower end, and a couple more trees at our upper end. Not bad? All right. So I think what we're going to do is we're going to probably end here. Let's save that. There is one more slide. So what I want you to do is, for homework, I want you to look through these situations and jot down your answers. Which distribution should we use? So here's our situations. Should we use the binomial distribution to model these data? Should we use the Poisson distribution to model these data? All right. And what I'll do is I will get our next homework assignment posted where you'll get to use the binomial and Poisson distribution. And again, we can do this by hand. I can show you how to calculate the probabilities by hand. We're going to use R. We're going to use R to calculate these. So our application part will be a little bit longer for exam number 2, because instead of calculating it by hand, I'll put those types of questions on the application part. But on the theoretical part, you might have situations like this. What distribution would you use, binomial or Poisson? All right. All right. Your exams, if I don't get them back on Friday, you'll get them back on Monday. All right. So we'll get them done. We'll get them graded. And we'll get them returned.
Do we turn the probability? It's okay if it's on paper.
Yeah. So the probability, if it's on paper, you can give it to me, or you can like scan it and upload it. I think I made that an option as well. So.
Friday or Tuesday? You said Friday.
What's the due date on Blackboard?
Last Wednesday.
It says last Wednesday.
Oh, I messed that up because we had the exam. I said no, we weren't going to do that until after the exam. Yeah,
that's why
we can make it due on Friday.
Okay,
We can make it due on Friday. Let's see if I can get that changed. I've done that a few times. I think I'm clicking on the correct day and it's not.
Double check the time too.
Yeah.
When you were showing the uniform distribution, it reminded me if you've ever seen like in shallow water, all the sunfish when they have their nests,
Mm-hmm.
they're like perfectly lined up and spread out and like spinning.
There's a reason for that.
Perfectly spread out, nobody's touching.
All right, October 1st. Yes, I did have it. Jeez, I can't believe it. We'll make that due at the end. Okay.